Hello, everyone. I'm here to present a library that Matt Rockland started and I picked up a few months ago. So it's about sparse arrays rather than sparse matrices, as Ralph mentioned in his talk. So here are a few shout-outs to people who have helped me throughout these few months that I've been doing Python. First of all, the Berkeley Institute of Data Science for bringing me out here, helping me give my talk. NumFocus and Numpy for picking up some of the other expenses that I had. Matt Rockland for really mentoring me since the start. And Rolf Gommers for introducing me into Numpy and really giving me a lot of support. And I'd like to thank every single other contributor to the library. So who am I? Well, I've been using Python since August 2017, so I'm a fairly new user, actually. I'm active on the Numpy mailing list. I've helped make quite a few architectural decisions so far. I've had no formal CS education. I've been a hobbyist programmer for a long time, but really no training. So the question, I guess, that comes to mind is, what are sparse arrays? Where do you use them? And the answer is, sparse arrays are arrays with a lot of null or zero elements in them. So a null element can be any element, but here it's zeros. For Boolean arrays, it would be false, and so on. And as you can see, this is an example array that has a lot of zeros in it. Real ones are really much bigger than this. Okay, so why use sparse arrays when dense arrays can do everything, theoretically, right? Okay, so the main two reasons are you have less memory usage and more performance. So since you only have to store non-zero elements and somehow a notion of their position somehow, you use a lot less memory than you would for a dense array. And you get more performance out of it because for memory operations, you can just skip over the zeros. You don't store them, you don't think about them, it's faster. Okay, where do you find sparse arrays? Think of any physical system that's loosely coupled, that doesn't have too much coupling between its various states or various components. So think of adjacency matrices or transition matrices of Markov systems, practical Markov systems. This is a very good example for sparse arrays. Think of solving systems equations. You get dense or sparse gradients, or maybe you could even get sparse Jacobians when you do solutions of these equations. Finite state controllers have matrices that are or arrays that are very sparse. And I just see matrices of graphs because graphs are usually, well, they're not really highly connected in most situations. So the standard solution to sparse arrays in the scipy ecosystem has been scipy.sparse for a very long time. And that's fine and feature complete, but it has a number of problems like Ralph mentioned. So it's limited to two-dimensional arrays, unlike the ND array interface, which has n dimensions. We also tended to adopt a design-first perspective from the start, so I always posted in the scipy mailing list when we had any kind of large design decision to make. We use NumPy protocols to ensure as much compatibility as we can with ND arrays. So as a result, a lot of functions that work on NumPy arrays work on sparse arrays out of the box. Okay, so with that, I get to the bulk of my talk. The first thing is how we store them currently, how we perform element-wise operations on them, reductions, indexing, transposing, reshaping, and master extents of products. I would like to emphasize that these aren't the only features we have right now. There are a lot more. These are just some of what I would like to cover. Okay, so storage format. We talked about storing a sparse array, and the simplest format for n dimensions is basically the coordinate format. It can be easily generalized to n dimensions. So, for example, you could see this matrix here, and you could see, for example, the 3 in the top row has a row index of 0 and a column index of 2, and the data is 3, and similarly for all the other indices. We also say that the density of such a sparse array is 0.25 because 25% of the elements are non-null. Let's talk about element-wise operations here. So suppose we want to add 2 sparse arrays, and remember that only the non-zero elements are stored and only their positions are stored. We don't really have an array that we could loop through to do this. So what we do is we first identify the elements currently in our library that are non-zero for both arrays. So those are highlighted in yellow here. And we perform the operation on those. Great. Then we highlight the elements that are 0 in one array and non-zero in the other. And similarly for the third array as well. This gives you 3 groups of elements that you would perform operations on. And by combining these back and resorting them so that they're in canonical order, you get back the result array. Another optimization that we had in this library, and let me emphasize that this is a broadcasting scenario in Numpy if you're familiar with it, is that, and this is element-wise multiplication that we're talking about here, is that you could have very large broadcasting scenarios. So let's talk about 2 sparse arrays being multiplied, and one of them has to be broadcasted to a very large dimension. What we used as an optimization here is that this yellow 3 would be matched with 1 time with any of the zeros and 1 time with 1. And basically what our algorithm that we used would realize is that when you multiply 3 with 0, you get it 0. So it doesn't have to be actually stored in the result array. And so you kind of skip over doing it 3 times and just do it once. And remember that in a real situation, this may be quite a lot larger. So here are some more details if you're interested. We use the array ufunc protocol so that universal functions work out of the box on sparse arrays. For n input ufuncs, this algorithm is generalized, so we use 2 to the n minus 1 batches of processing. That's 1 for each off and on array, and 1 removed batch which says, hey, all arrays are off, this is supposed to be null anyway. We're working on a way to loop through the coordinates so that's faster and you only loop through the arrays once. And sorting is slow. So right now about 30 to 40% of the time in all operations is usually taken up by sorting. We're working on switching to a radix sort from quick sort, which should be quite a lot faster. And well, the problem is that a lot of operations on sparse arrays actually give you dense arrays. So think of taking the cosine, which maps 0 to 1. We're working on making those sorts of errors lower and supporting more use cases. But in the end, you want to make this an error so that you don't get a dense matrix at the end and get a lot of performance degradation, which can be a lot harder to debug than just raising an error. Let's talk about reductions now. Reductions are actually quite challenging to do in general, but we have managed to implement a subclass of all reductions for sparse arrays. So addition is easy. Summing along the rows is easy. You just sum all the non-zero elements, right? Let's talk about something more interesting. Let's talk about taking the product along the rows. So what we do here is we take the product of the non-zero elements, and we also store some additional marker that says, hey, there are additional zeros here. That gives you this. To remember that the third row was non-zero, so we don't even store it. And for the 6 and the 2, you get a marker that says there's a 0 after this, and for the 5, you say this has no zeros. So you reduce an extra time with 0 where you get a yes or a true. And what you get in the end is you get this out, which is the correct answer for products. For those of you following this algorithm, you may have realized that these are the restrictions that you would have. But in practice, a lot of reductions are supported. Sum, prod, min-max, any, all are all supported. In the future, we plan to add argmin and argmax as well. We also use the array ufunc protocol for reductions. So sum, min, all ufunc reductions work with the restrictions that we specified before. Sorting takes up a lot of time still, so we're working on improving that. And general reductions are implemented by transposing and reshaping to a two-dimensional array and doing it in the reverse order at the end. Let's talk about how we index sparse arrays. So suppose we want to grab this yellow 3 here. And what we can do is, since the coordinates are all sorted, we could first grab the row, and then we could grab the 3 via a simple binary search, right? Because they're all sorted. But we could also get a situation like this, where, for example, you get a lot of elements that you have to address. And so addressing each of these rows is one binary search, and addressing each of these elements is another binary search. So in the end, you get about 12 binary searches, which is more than the number of non-zero elements in this array, right? It's crazy. So what you can actually do is you could directly filter out the coordinates. So you can filter out by rows, that gets rid of the 5 there, and you could filter out by columns, which get rid of the 1 here, and then you apply a simple transformation and you're back to simple array, the elements that you want, and then you could calculate the new coordinates. So in practice, what we do is we follow a hybrid scheme where we weigh the number of expected binary searches versus the amount of elements which we'll have left and we would have to filter. And whichever one is faster, we just pick that one and roll with it. And the problem is that this is not fully compatible with Numpy in the sense there's no view. So everything is a new array, even a slice and even an integer index right now. And it's slower than Numpy because we actually have to do binary searches or sometimes filter coordinates. So that's not ideal. Transposing or reshaping works exactly as you would expect. For transposing, we simply switch the order of the coordinates and resort it so that it's still in canonical order. For reshaping, we convert the coordinates to a linear index and then convert back, and that essentially reshapes the whole array. And for matrix tensor products, we reshape both arrays into 2D. Multiply uses matrices using a BLAS implementation. There are BLAS implementations even for sparse arrays. And then we convert back to the required dimensions. We're actually looking for more people to start using this so that we could get more feedback on what's important and what we should prioritize. So you're welcome to use it. The API is not yet stable at this point. It's mostly stable, but not quite. It has really comprehensive documentation, so we have that going for it. It's thoroughly CI tested, so there should be very little bugs, if any. Planned features that we have for this library is right now, COO is the only format that's supported. We also have the DOK format, which is more writable. But we plan to have a format that's a generalization of these formats, which would make sense in a lot of scenarios and for a lot of libraries that expect this format, such as, for example, scikit-learn. We tend to get a lot of results in sparse errors right now, sometimes in some operations. So we intend to make those lower by having a number of features. We plan to support more of the Numpy API through protocols. I'm really pushing protocols at this point because it's useful not just for my library, but also for Dask and XArray and a number of others. We would welcome contributions if anyone is interested. Just talk to me, find me. I'm always available. And like Ralph said, we're planning on integrating into scipy at some point once this library is more feature complete and the API is more stable. I thank you for your time, and I'd be honored to take any questions anyone may have.
Thanks very much, and welcome to the Python family. And I was wondering, we have time. We have time for several questions, and we have one mic over there. I'm over here with one mic. I'm willing to run around a little bit. Who is a first-time scipy attendee? Anyone? First time? A few hands. Okay, cool. We have 800 people registered for the conference this year, which is quite an incredible growth for the conference. Okay, I don't see it. All right, please.
Hi, thanks for your talk. I had a question. I guess you kind of briefly mentioned it on the last slide. You have like that error that pops up, like, result not sparse. So, like, if you add a bunch of sparse arrays, like.
There's some echo in the sound. Okay, can we fix that? There's some echo in the sound. Okay. I can't hear his question properly.
Could you repeat your question? Sorry.
So on the last slide, you were mentioning the like result not sparse. Mm-hmm. So is that like when you like add a bunch of sparse arrays, like you get a result that's like a dense array? What's the plan going forward to kind of deal with those types of things? Like, oh, this won't be sparse. Let's just convert it to like a dense Numpy array.
This is really a by dense result not sparse errors, we only raise them when a function is mapping a 0 to a non-zero currently. So things like taking the cosine of a sparse array, or maybe like 1 minus a sparse array that would make it dense. So we really don't raise it if you add a bunch of sparse arrays, because that would keep the result sparse. And we also raise an error when, for example, you're performing a reduction and an axis that is entirely composed of zeros reduces to a non-zero axis. So those are the main scenarios that you get that sort of error.
I have another question over here. Let me pass the mic.
Oh, go ahead. Yeah, sorry.
Just a quick one. So are compressed row storage and column storage, are they implemented already, like a conversion at least, or not yet?
We do support conversion to scipy, CSR, and CSC matrices, and from those formats as well. But those formats aren't natively implemented in this library. It is planned, and it is a prioritized feature as of now.
Thank you.
Please.
Great talk. I was curious, so you mentioned converting to Numpy arrays, and Numpy has this protocol, this dunder array protocol. Do you use that protocol for making sparse arrays convertible? Is that useful or not?
Yes, I have been using the array ufunc protocol extensively. It's used to achieve intercompatibility with NumPy. So the array ufunc protocol, I use it for reductions and for ufunc applications, universal functions. And me and a number of other people are also working on the array function protocol, which allows you to dispatch an arbitrary function to any kind of object. So we plan to use that one as well. Yeah.
Okay, thanks.
Okay, I have another question over here.
Hi, yes. Roger Surwey here. My question is, you have this sparse matrix because you want to eliminate zeros, and you're raising a dense error matrix if you go through a cosine function. What if you had the ability to say it's a sparse matrix with a constant offset, so you can have a cosine function, and it will still be sparse as everything adds a 1 to it?
Yes, that is actually a planned feature. We call it arbitrary fill values. So the idea is that we actually store the null value and allow it to be something other than 0. And if like 0 is mapped to a 1, for example, like in 1 minus x, then we store the fill value to be 1. It is a planned feature, yes.
Anthony, you have a question over there? Is that Anthony Skopats? I can't see it. No, it's Hameer. Okay. Andrew.
Do I really look like Anthony?
No, but you are so related that my mind, made the connection.
Oh, okay. So is the plan for this to eventually be a replacement for scipy.sparse?
That is the plan, yes.
So
But
are you going to implement like all the linear algebra as well?
I don't plan to implement it myself, but there are a number of C and Fortran libraries that already
Well,
do
that-
it,
that's
but
what
I
mean.
do.
Like, are you going to integrate with this like?
Yeah, we do
UMF
plan
and
to
all that?
wrap those libraries.
Okay, another question here.
Thank you. I suppose my question is sort of related to the previous question. I think the people are interested in sparse algebras, sparse arrays, not only because they offer more efficient storage, but also because they offer quite a savings in performance when you perform certain operations. And because efficiency is at stake here, you want to go native and go interface to libraries. So the question probably is, do you foresee any developments where you would allow to use libraries for efficient implementation of linear algebra or something else like core operations, like Numpy does for certain things, certain ufuncs may be implemented in C. Is there a way for sparse to support a C interface to improve efficiency? Thank you.
Good question. So ufuncs already are implemented. Ufuncs work right now. They're not as fast as in scipy.sparse, but they are implemented. And we also are working on making them faster. There are some, actually we use Numba as the backend, as the fast computational library for this project. And there are a few features that we require on Numba's end before we can move forward with some things. But those features have come very recently in Numba 0.39. So their ufuncs applications should be faster. And about linear algebra, we don't plan to implement linear algebra directly inside our library, but as I'm thinking that I've talked with Ralph, and that seems to be his view as well, that once we pass a point where we have all the essential data structures implemented, then scipy, I will work with scipy developers, and I might work directly in scipy to actually wrap the core linear algebra routines with sparse arrays.
Any more questions? Very exciting project, especially for the PDE people in the room. So thank you.
Thank you.
Final question? Yes? No?
Final question.
I heard,
just
yes, we do have one. Okay.
Speaking to your experience as a new contributor to the whole scipy ecosystem, could you speak to how you would try to encourage other people to get involved and start contributing as well? I mean, it's not a question that has anything to do with sparse arrays, but something I'm really concerned about.
So I would say that I would do what Matt and Ralph really did with me. So I would encourage someone and not tell them that their code is bad, instead tell them how they could improve it. And tell them that this is a good effort, right? So yeah, that's the best you can do. You can encourage someone to get involved. You could invite them to get involved, but in the end, it's obviously their own choice. But obviously, the better the community, the more welcoming they are, someone will want to get involved.